Okay, so here's another question, and it's the same type of question as the other one. So we're given a language, and we're asked to determine if the language is decidable, recognizable, both, or neither. And we need to explain/prove our answer. So first, let's go over what a language actually is. So it's all strings over alphabet 0, 1, where the string is non-empty, so its length is at least 1, and the number of ones in the string is a multiple of the number of zeros in the string. So for instance, if we had this string over here we have 6 ones and 3 zeros. I want to check if the number of ones, 6, is a multiple of the number of threes, which is 3. And 6 is in fact a multiple of 3, and so this string would be in the language. So again, to check if the string is a member of this language, we need to check if the number of ones is a multiple of the number of threes. But how do we do that generally? Like for example, say we had this many ones and this many zeros, so 78 zeros. How do we check if this is a multiple of this? Well, one way we could do it is by dividing the two numbers. So if we have 12, we want to see if 4 is a multiple of 12. What we can do is divide the two numbers and check if the result is an integer. So 12 divided by 4 is 3, which is an integer, and that means 12 is in fact a multiple of 4. If, for example, we also had 9 and 4, to check if 9 is a multiple of 4, we divide the two, and we get 2.25, which is not an integer, and so 9 is not a multiple of 4. So that's one way of checking if one number is a multiple of another. And one thing you can notice is that division is actually just repeated subtraction. And so another way of checking is by repeatedly subtracting this number from this number and seeing if we ever reach 0. So if we do this, so 10 minus 2 is 8, 8 minus 2 is 6, 6 minus 2 is 4, 4 minus 2 is 2, and then this is 0. So we reached 0. Therefore 10 was a multiple of 2. If this was instead 11, then what would happen is we'd go to 9, 7, 5, 3, 1, and minus 1. So we didn't reach 0. This will never reach 0, and therefore 11 was not a multiple of 2 because it didn't divide into 2 evenly. Okay, so that's how we check if one number is a multiple of another. And the next thing you need to ask yourself is, can a Turing machine do this? Well, again, a Turing machine can do anything that a computer or human can do in terms of calculations. And because a computer can definitely divide two numbers and see if the result is an integer, then so can a Turing machine. And because you can do this calculation as well, like we just did, so can the Turing machine. And therefore, we know that the language must be decidable. And because it's decidable, it should also be recognizable. So therefore, it's both. But we just need to sort of write out a way that describes how a Turing machine would do it. So we're going to say that the language is both decidable and recognizable. And now we need to write out the steps that the Turing machine that we're trying to construct would take to decide this language. So again, we can just use an algorithm. And the one we could use is the repeated subtraction one that we just mentioned. So we could find a way to sort of simulate that on a Turing machine. So let's imagine this was our tape. And the input was maybe this. Just imagine that was the input. So what we want to do is sort of get the counts of ones, the number of ones in the string, or the number of zeros, and then see if the number of zeros divides into the number of ones. So how could we count the number of ones and zeros? Well, we could use an extra tape or two. So we could have tapes that contain all the ones and a tape that contains all the zeros. And that would sort of be equivalent to counting them. So let's do that. So how do we get all the zeros onto a separate tape? Well, we can go left to right on the main tape. And then copy over all the zeros as we see them. So we're here, we see a zero, copy it over, move the readheads, keep scanning until we see a zero, copy it over, keep scanning, see a zero, copy it over, and so on and so on. Okay, let me just remove this zero. There we go. So we reach the end, and now we do the same thing but for ones and do it on the other tape. So copy over the one, copy over the one. Should have moved the readhead first. What the hell just happened? Oh. Okay, copy over the one. And so on and so on. Okay, that's all the ones. Copy them over. And now our goal is to check if the number of ones on this tape is a multiple of the number of zeros on the other tape. And one thing I forgot is that there should be blank symbols here, so let's just pretend like I put them there. Okay, now how do we check if the number of ones is a multiple of the number of zeros? Well, as mentioned before, we can use one of the algorithms we discussed. So for this one, I think it'd be easier to just use the repeated subtraction method. So we're going to try and remove 3 zeros at a time from this tape and see if we eventually reach a case where after removing one batch of zeros, we have no more ones left. So let's do that. The way we'll be removing ones is just by like crossing them out. So basically for every zero, we remove a one. Let's do that. We start the readheads at the very start of both tapes. Then we see that the character under the zeros retape is a zero. That means we want to cross out a one. So essentially we're just changing the symbol to a crossed out one to represent it being removed. Remove both readheads, to the right. We see that there's another zero that we need to match, and so we cross out. Okay, move both. Another zero, so we cross out. Okay, move the characters over. And we see that we reach a blank symbol on the zeros tape, and that means we removed one batch of zeros. Sorry, one batch of ones. And so now we want to check if we removed all the ones. And because the character under the read head is yet another one, we still have more ones to remove. And so we need to repeat the procedure of subtraction again. So we do the same thing, cancel out the one, move on to the next. Okay, we have another zero to cancel out, sorry, another one, so we do that. Okay. Okay, and then we notice that we have finished up a batch of zeros, and at the same time, there are no more ones left to cancel because we reached a blank symbol. So we've processed all the ones, and at the exact same time, we just happen to finish a batch. That means that we managed to cleanly divide the number of ones by zeros, because this is essentially the same as reaching zero as before. Like if we had 6 and 3, then we take 6 away, we take 3 away from 6, we get 3, then we get 0, and because we have 0 after repeatedly subtracting, that meant that 6 was a multiple of 3. So that's like the same thing that's happening over here. And so in this situation, we would accept. Now let's look at a situation where we would reject. So we sort of get what's going on in that case. Okay, now imagine that we had 4 zeros instead. Let's do the same procedure. Cancel out 4 ones in each subtraction process. So cancel out, move readhead, cancel out, move readhead. cancel out. Oh my god. Okay, now we notice that we reach a blank symbol in the zeros tape, so we finished a batch of ones, which means we need to check if there's more ones remaining, and there are more ones remaining. So we need to repeat the process of subtraction again. Okay, cancel out. Cancel out again. And what we notice is that the ones tape has reached a blank symbol, but the zeros tape, the read head on the zeros tape, is not at a blank symbol, which means that we still had a zero to cancel out in the current process. And so what that means is that the number of ones doesn't cleanly get divided by the number of zeros, which means that we reject in this case. So this would be equivalent to having 6 and 4 and checking if 6 is divisible by 4. We would have 2, that would reach -2. And because we didn't reach 0, that means that 6 is not divisible by 4. And so in this case, we'd also reject. So what we're looking for acceptance is that the read head on the ones tape reaches a blank at the same time as the zeros tape. And if that isn't the case, if we have a blank on one tape, but not a blank on the other tape's read head, then we know that it's not divisible. So let's write that out as an algorithm. So construct TM that follows the following steps. And one thing to mention is that because the string is non-empty, we need to check that because the question says the string must not be empty, we need to check for that. And another thing to keep note of is that if the number of zeros we have is 0, then we need to reject because we would be sort of dividing by 0, which isn't allowed. So we need to check the string is non-empty and that there is at least one 0. So let's do that. So step 1, we're going to check that input is valid. So first, we're going to check if first character is a blank. Because if the first character is blank, then the input was empty. And if it is blank, then we want to halt and reject. Okay, next we want to check if there's at least one 0. So scan through the tape until first blank. So that would be the end of the input. If no zeros were encountered, then we want to halt and reject because we can't have 0 zeros. There we go. Now we move on to the part where we do this repeated subtraction stuff. So as mentioned before, oh wait, let me just say that we reset the retard. So as mentioned before, it would be really nice if we could just copy over the zeros and ones onto separate tapes. So let's do that. So use a second tape, and therefore we're using a multi-tape Turing machine. And onto the second tape, copy over each zero that is on the main tape. So to do this, we scan the main tape from start to first blank, so the end of the input. And for each zero, we write a zero onto the second tape. And then let's call this tape the zero tape, just so it's easier to refer to in the future. Okay, let's do the same thing, but for ones. So use a third tape. Follow the same procedure as here, because I don't want to rewrite all that stuff. So same procedure as in 2.a to copy over, copy over all ones on the main tape to the third tape. And let this tape be called the one tape. So that's the one. There we go, one tape. Okay, now we have all the characters copied over to separate tapes. Let's now move on to the actual subtraction part. Okay, now, just to make it clear to the examiner, it would be a good idea to write a little footnote on what we're doing. So we're doing repeated subtraction. Whoops. Repeated subtraction of the number of zeros. I'm just going to write hashtag for short. From number of ones to check divisibility. So that's divisibility. Okay. What the hell's going on? Okay. So now, let's say that for every zero, remember that we're going through all the zeros in the zero tape and trying to remove the corresponding one to simulate subtraction. So for every zero on the zero tape, so here we're just scanning from start to end, and by end I mean the first blank symbol. The first blank. We want to cross out a 1 on the 1 tape. And move the read head to the right by 1. So by RH I mean read head. And now, at this point, we've moved both read heads on the 0 tape and the 1 tape by 1, and so we want to check that the tapes are on blanks or not. So we want to check if they're on blanks or not. So if the 0 tape read head is on a blank, then we finished a batch of zeros essentially. We have subtracted, well, not we, but the TM. Of zeros. And now we want to see if there's ones left to remove. So if there are still ones remaining, and the way we know that is that the read head of the ones tape is on a 1. Then we just want to repeat from over here. So we're repeating from 3.A. And yeah. And if there isn't a 1 remaining, I'll just say otherwise. So if there's no 1 remaining, and we already finished subtracting a batch of zeros, that means we accept because the number of 1s was cleanly divided by the number of zeros. Otherwise, halt and accept. As the number of 1s was cleanly divided by the number of zeros. Okay, so if the 0 tape read head is on the blank, we do all this, and if it isn't on a blank, then all we're checking for is that there's still a 1. So what I mean by that is if we had this 0 tape and the read head is not on a blank, so this one failed, then we need to check if there is still a corresponding 1 to remove. So if the read head is not on a blank, we need to check that the 1 read head is also not on a blank. Otherwise, there's no 1 to remove. If that makes sense. So we're checking for this situation where the 0 read head is on a 0, but the 1 read head is on a blank. So this is corresponding to this. If the 1 tape readhead is on a blank and the 0 tape 1 isn't, then we know that we still need to subtract. We haven't finished subtracting a batch of zeros. Sorry, my pen is bugging out for some reason. We still haven't finished subtracting a batch of zeros, but there are no more ones left to subtract. So in this case, we want to halt and reject. Halt and reject because the number of ones was not cleanly divided by the number of zeros. So was cleanly divided by number of zeros. Okay, that's a bit messy. So we should actually give this thing a name and then say that if the 1 tape readhead is not on a blank and the 0 tape readhead is also not on a blank, they want to just continue crossing stuff out. So let's say that otherwise, if it isn't, go to step 3.b. So that's 3.b. Okay, so basically, just to quickly reiterate, we go through every 0 in the 0 tape, we cross out a 1 on the 1 tape, and then after doing this, if the 0 tape readhead is on a blank, that means we finished subtracting a batch of zeros, and we need to check if there's still ones remaining. If there are ones remaining, we sort of start a fresh batch of zeros and do this for loop again. Otherwise, we halt and accept because number of zeros, so the number of ones was cleanly divided by the number of zeros if there's no ones remaining. Next, if the 0 tape readhead was not on a blank, so it's still on a 0, but the 1 tape readhead is on a blank, then we haven't finished subtracting a batch of zeros, but there's still ones that should be subtracted. And so there's no more ones left to subtract from. And so we halt and reject. If this isn't the case, we just need to continue crossing out ones, and so we go to 3.b. Okay, so that's it for the steps part of the algorithm. So this is basically just the main algorithm, but we still need to go over the concluding statement where we say that the algorithm can be completed in a finite amount of steps, and so it takes a finite amount of time, and therefore the Turing machine will always halt and never loop. Another thing I want to mention is that all this stuff is really detailed, there's a lot of writing. You could probably make it more concise and maybe higher level and not go into this much detail, then it should be okay. But just to be safe, if you have enough time in the exam, try to make it as detailed as possible so that the examiner knows for sure that what you've written is correct. But if you're struggling to come up with an answer, you can write out something that's less verbose, so you could make it even higher level. So instead of writing out all these details about scanning through stuff, you could say something like, have the Turing machine count the number of zeros and the number of ones, and then through repeated subtraction, check the divisibility of the two numbers. So you could just say, repeatedly subtract the number of zeros from the number of ones, and then if the number of ones eventually becomes exactly zero, accept, and if you reach a situation where it sort of becomes negative, then reject. But obviously you can't have a negative number of ones on a tape, so you'd have to explain that in a different way. But I hope you sort of get the idea. Okay, so let's now do the concluding statement for this one. Okay. So let's say that because The algorithm takes a finite amount of steps because we always reach the base case of running out of ones. So we'll always run out of ones if we subtract enough times. So just to reiterate, because we will eventually run out of ones if we repeatedly remove them, this algorithm will always take a finite amount of steps. So that's what we're saying. So because it's a finite amount of steps, the Turing machine will halt in finite time, so it will always halt on any input, and the outputs of the response, like rejection or acceptance, will always be correct. Because the Turing machine basically just checks for divisibility. So it checks if the number of ones is divisible. I'm just going to write it out short like this. So divisible by the number of zeros, which is the same as checking that the number of ones is a multiple of the number of zeros. So therefore, by construction, we have created a Turing machine that decides a language. So L is Turing decidable, which means it is also recognizable. What is going on with my pen? One sec. So it is both decidable and recognizable. So that's the full answer. I'm just going to leave the screen here so you can read it if you need to. And then back here, even though the handwriting is super messy. Okay, there we go. Again, you could probably make all this stuff a lot neater and more concise, but this should be good. There we go. Okay, if something wasn't clear, then just let me know.